Hello everyone, welcome back. So let's do an example. So what we want to find is the distance s when this block stops. What we see is that it's got a velocity initially of 5 meters per second. There's a force of 100 newtons being applied to it, and that spring stiffness coefficient is 200 newton per meter. Now the spring is initially not stretched or compressed when s is equal to 0.6 meters. And the block has a mass of 10 kilograms. Ooh, we've got a lot here. Now, keywords we want to see here, not stretched or compressed, and smooth. That gets rid of all the friction there, and this is saying we don't have any initial spring force. So I'm going to let you go off and do this on your own, as normal. But before that, let me give you a plan. Now this force problem involves forces, velocity, and displacement, so apply the principle of work and energy to determine S. You're like, but how do I do that? It's not that hard. Look at the things that are going to be causing work. Might want to draw a free body diagram. But try your best, and then come back and watch the rest of the video, and we'll do it together, okay? So 3, 2, 1, and you've returned. So let's try it out together. So we're going to go from position 1 to some position 2, which we don't know, which we'll just call S2. Also, the normal force doesn't actually do any work because it's perpendicular to the displacement. So we know that our initial kinetic energy and our final kinetic energy, we know what the difference is going to be because this is going to be 0. It's going to stop at that point. And we know what this one is because we know the mass and the velocity initially. So we need to figure out what the work is going to be. Now, work of the 100 Newton force is going to be simply 100 times the displacement because they're in the same direction. Work of the block weight, yes, the weight does work because it is partially in the direction of my displacement, would be simply the mass times gravity, which is the weight, times my displacement, sine of 30, because it's not perfectly along that direction. Finally, the work of the spring is a negative work because it is pulling it backwards. It is not like that it's moving that direction. And it will be 1/2 times the stiffness constant times my displacement squared. Okay, so if I add all these together, what I'll see is this fairly long equation. We plug it all in, and we see that my initial velocity, my initial kinetic energy, will be dissipated by and added to by all these things, and then it will eventually equal 0. So if we want to, we plug all of our numbers in, and we can begin to solve. Now there will be 2 roots to this, and one of them will be negative. So choose the positive root. And that positive root would be that S2 equals 0.6. Sorry, S2 minus 0.6 is equal to 2.09 meters. So S2 would be 2.69 meters. Now I know that this is no fun whatsoever. But this is still just your regular negative b plus or minus b squared minus 4ac all over 2a. That's all you're doing there. It's not fun to write, but it works. So use it to your advantage. If you're wondering how you can do that, it's because I'm using this as my variable rather than just trying to get S2 as my variable. I could multiply it all out and it would still work. It's just you don't have to necessarily. Simplifications like that can be a lifesaver. You don't necessarily need to solve for S2 directly. You can solve for S2 minus something and then at the end solve for S2. Okay, so I believe that's everything. It is. So thank you for listening, and I'll see you all next time. Bye-bye.